So students, in this lecture we are going to learn about the entrance region, how a flow basically enters a region. But before we go for entrance region, we should revise what is slip and what is no slip condition. Slip and no slip. When we talk about slip, it means that the fluid is slipping over each other. So let's say I've got a pipe, okay, and a fluid with uniform velocity is entering this pipe. So if I'm going to say that there is slipping, it means that there is no friction. When there is no friction, then the fluid is going to slip. It means that the velocity, let's say from 0 to 0.1 would be 1 meter per second, and then from here to here as well would be 1 meter per second. So it's going to be just a straight line velocity profile. Okay. But what happens, this is the case for no friction. What happens if I have friction? When you've got friction and let's say uniform velocity enters this pipe, then what happens is that because of friction, let's say this is 0.1, this is 0.2, so my fluid particle, because of the friction, cannot reach 0.2 earlier, so it will stay here, and then it is going to drag the other particle who is moving in front also backwards. So in this way, what is going to happen is that we are going to get a velocity profile due to shear effects as a no slip condition. Okay, and this velocity profile might look like something like this. At this point there is velocity 0, the fluid sticks to the surface and it attracts the other layer towards itself. Okay, so the velocity, so consider that I have got a pipe. Okay, I've got a pipe. Okay, let's consider the lower portion of the pipe. Okay, so imagine that the fluid with uniform velocity is entering the pipe. Okay, now here we have got friction. This pipe has got friction, which means no slip condition. So when this pipe has got friction or no slip condition, then the fluid particles are going to stick to the wall. So in the initial region, let's say in this part, what is going to happen is that some particles will stick and some particles, and it is going to drag the second layer. Okay, but then there will not be a lot of effect on the other layers. Okay, so same goes here as well. It is going to affect some layers but not all of them. So what happens is that the velocity profile is basically changed initially, and but it remains constant in the middle, and then it is changed initially. What happens is that as the flow moves, as we move further distance, so let's say that this is the distance x direction, okay, and this is the radial direction or the diameter of the pipe r. So as we are going to move forward, what is going to happen is that more layers are going to be sheared away, and more shearing means that the shear layers are going to drag each other's back. So if I'm going to draw here, so if initially it was like this, then it is going to drag other layers as well. Okay, so the profile is going to look something like more curvish, then uniform, and then more curvish. So it is looking like this. So let's say that in the first part only 1 and 2 layers were dragged, and in the second part, as we move away from the entrance region, as we move in the x direction, then let's say 3 layers were dragged. Okay, so the flow now looks like this. So let's move further. So as we move further, what happens is that more particles are going to be dragged. Okay, so 3, then 4, then 5. Okay, and then the fifth remains constant, and then here also 1, 2, 3, 4, and then here is our velocity profile. Okay, so this is called velocity profile. Now what we want to say is that at this point the frictional effects were present, but above this point, if we look at this point, this here the velocity is same. It means that the frictional effects were not present. And if we look here, the frictional effects are present below this point. Above this point, the frictional effects are not present. Same goes here as well. Okay, and then there comes a time when the velocity profile becomes constant. Okay, so what we are going to do is we are going to join these lines, okay, like that. So this straight line is basically straight velocity profile. If you observe, the velocity profile was straight, and below or above these points, due to shearing effects, the velocity profile was changing. So this line is called boundary layer. Okay, so below this line, below this region, okay, this line, viscous effects, viscous or shear force effects are present. Okay, this is called velocity boundary layer as well. Okay, and in this region, in this green region, okay, if you see this green region here, the frictional effects are not present. Okay, because not all the layers can shear away, some of the layers slip within each other. Okay, so this region, the region within the green lines, is called irrotational flow. IRROTATIONAL, irrotational flow. Irrotational flow is also called core flow because it is in the center of the pipe. Okay, so remember, whenever a fluid enters a pipe, there is basically a development of boundary layer. Within boundary layer, the viscous effects of, the friction effects of, or the shear effects of the pipe are present, and above that boundary layer, the flow does not have any viscous effects, and this is called irrotational flow. Frictional effects are negligible, and the velocity remains same. So you can see the velocity profile is same. So this is all about velocity boundary layer or boundary layer region. So what happens after boundary layer develops? So basically what happens is that after this velocity profile is developed, then it remains same, constant throughout the pipe. Okay, and once it remains constant throughout the pipe, then it is called fully developed flow. Okay, because the flow or the velocity profile has developed, so it is called hydrodynamically fully developed flow. Okay, and the point of the distance from here to fully developed region. Okay, so let's say I'm going to change the color. So distance from here to the point where the flow becomes fully developed, okay, is called hydrodynamic entrance region. Hydrodynamic entrance region is the region from the pipe inlet. It is the region from the pipe inlet to the point at which the velocity profile is fully developed, to the point where the velocity profile is fully developed. This is called hydrodynamic entrance region. Okay, so hydrodynamic entrance region. Okay, and this length, this is called hydrodynamic entry length, denoted by LH. Okay, hydrodynamically entry length. Okay, so after this point, okay, the flow is fully developed. So it is hydrodynamically fully developed flow. A flow is said to be fully developed when the normalized temperature profile remains unchanged as well. So we need to understand that the temperature profile and the heat transfer is also constant. So these are something which we need to keep in mind, these terms: developing velocity profile, a fully developed velocity profile. So if I'm going to look at these first three profiles, these are developing velocity profile. Okay, developing. They are trying to develop to uniform velocity profile. Okay, so these three are called developing velocity profile, and once it is developed completely, okay, and the velocity profile remains unchanged, then this is called fully developed velocity profile. So let us look at an example of an aerofoil shape. Okay, this is an aerofoil shape. Okay, if you see the wings of an airplane, usually they are also made of this aerofoil shape. So what happens is that when the plane is moving forward, the air basically at uniform velocity strikes the aerofoil. Okay, so let's say that this is all fluid with an average velocity, constant average velocity. Okay, as the air is going to strike this aerofoil, what is going to happen is that here there is no slip condition. So what happens is that some of the fluid is going to stick to the surface. So velocity will be 0 here, but then it will try to increase and then increase. So it is going to look something like this. So you can observe here as well, this is the velocity profile, it is constant, but then it becomes, due to no slip condition, it changes. Okay, and if I'm going to make a boundary layer, it is going to look something like that. But because this is something which is observed at very small level or prototype level, so the dimensions might change. So you can observe this phenomena now. You can see this is decreasing. Okay, here you can see it is changing. No strict condition can be observed here. Okay. So let us take a look at some of the lecture notes, and here is an introduction to the entrance region. Okay, this is something which we have covered just now, is that between entrance and fully developed flow, so between entrance and fully developed flow is a region called hydrodynamic entrance region. So this region is called hydrodynamic entrance region. Okay, what is this saying is that a uniform velocity profile enters at entrance. So just at the entrance you can see that the velocity profile is uniform. Okay, because of the no slip condition. So what happens is that when the fluid strikes the boundary, okay, because of the no slip condition, the friction at the wall reduces the velocity, so the velocity is getting reduced. Okay, and to conserve the mass, so the mass flow rate at the entrance and the mass flow rate at the outlet is same. So to have the same amount of mass, the area under this curve, so if I have this velocity profile uniform, and because there is some shearing occurring, so what is going to happen is a velocity profile of something like this is developed. Okay, and in order to have the same mass flow rate, okay, the area under this curve should be same. So the area under this curve should be same. So that is why to have conserve the same amount of area, the velocity basically it decreases here but then increases here. Okay, that is why in the last we get an increasing velocity profile shape. So to conserve the mass, the velocity at the center increases and compensate the velocity decreases, which has decreased at the wall. So it follows that as the fluid moves deeper, okay, the velocity near the wall decreases further, and near the wall the velocity decreases, whereas at the center the velocity increases. Okay, both up, down, left, right. So if you look here and here, okay, the velocity profile increases till it merges with the other side. So this velocity profile, if I'm going to change the color, okay, so the velocity profile for the upper portion and the lower portion increases until it merges at the center. Okay, so this after this part the flow becomes fully developed. This is when the velocity profile stops to develop as it flows deeper inside the pipe. So after this region, the velocity profile will remain same and constant, similar to the fully developed flow. And what is important to note that since the mass flow rate in and mass flow rate out is same, so the average velocity, whether it is developing flow until here, so until here it is developing flow, or after this which is fully developed flow, this is developing and this is fully developed flow, the average velocity is same. You can see that this is because of the conservation of mass. So if you guys would like to observe the pipe flow and how it develops, you can have a look at this example. Here you can see the velocity profile is average, and then here you can see that there has been some decrease, and then it becomes average, and here at this point there is no slip condition, something like that. So here the profile looks like that. Okay, so you can observe this here. This is how it moves. So let's take a look at hydrodynamic entry length. And if you take a look and consider fluid flow in hydrodynamic entrance length, so if I'm going to look at this hydrodynamic entrance length, okay, so what happens is that wall shear stresses, TW, wall shear stresses, okay, are the highest. So initially the wall shear stress is very high. It is the highest at the pipe inlet where the thickness of the boundary layer is smallest. So you can see that the thickness of this boundary layer is smaller when the shear stress is high, and the thickness of this boundary layer is small. Okay, so what happens is that this thickness of the boundary layer increases, okay, and the amount of shear stress decreases. Okay, therefore what happens is that the pressure drop is higher at the entrance region. That is why we are studying this LH, the hydrodynamic entrance line. Why? Because the pressure is dropping higher. So if the pressure is 1 here, then the pressure increases to P1 plus some value x. So it decreases to some value x. Okay, so there is a pressure drop. So the pressure drop is higher in the entrance region of the pipe, and the effect of entrance region is always to increase the average friction factor. So for the entire pipe, the average friction factor increases. This increase may be significant for short pipes but negligible for long ones. So let's say that if I've got a very short pipe, okay, and I want to see the pressure loss, okay, then the hydrodynamic length is quite large compared to the size of the pipe, so the pressure loss will be higher. Okay, there will be some decrease in pressure. But if my pipe is very long, okay, compared, and my entrance region is only this, okay, then the pressure drop due to hydrodynamic entrance length LH will not be very high. Okay, the pressure drop will be due to only the frictional effects of the pipe, not due to this entry length. So in this case, the LH can be ignored. So the significance of LH is that this LH is very useful in calculating the loss of pressure in pipes when the distance or when the size of the pipe is small. So the hydrodynamic entry length can be calculated differently for laminar. It has to be calculated differently for turbulent. Okay, why? Because when the initial velocity profile is laminar, then there are different formulas to be used for calculating the hydrodynamic length LH. Okay, Reynolds number depends on velocity, and for laminar flow, the LH laminar depends on 0.05 times Reynolds number multiplied by the diameter of the pipe. Okay, and if let's say the flow is turbulent, there is a rapid mixing. Okay, so what happens is that the LH is basically considered equals to be 10 times the diameter of the pipe. So this is internal diameter of the pipe. So these are formulas to calculate LH, hydrodynamic entrance length.
After the creation of boundary layer, there is a unique types of velocity that fluid particles goes through. We call it velocity profile. Let us visualize it. Consider a fluid entering a circular pipe at a uniform velocity. A fluid in motion comes to a complete stop at the surface and assumes a zero velocity relative to the surface. That is, a fluid in direct contact with a solid sticks to the surface, and there is no slip. This is known as the no-slip condition. The fluid property responsible for the no-slip condition and the development of boundary layer is called viscosity. The layer that sticks to the surface slows the adjacent fluid layer because of viscous forces between the fluid layers, which slows the next layer, and so on. So, the flow region adjacent to the wall, in which the viscous effects are significant, is called the boundary layer. But in the blue region, there is no boundary layer surrounded, so the frictional effects are negligible, and the velocity remains essentially constant in the radial direction. This blue region is called irrotational flow region. As the fluid passes by, the thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center and fills the entire pipe. Remember, at first, water velocity is just a function of pipe length and pipe radius, but when the boundary layer fills the entire pipe, then velocity will just be the function of pipe radius. Keep that in mind. So, when velocity varies only on radial direction, then velocity profile develops, which makes calculation easy, as it only depends upon one direction. That is pipe radius. The region from the pipe inlet to the point at which the velocity profile is fully developed is called the hydrodynamic entrance region, and the length of this region is called the hydrodynamic entry length.